fourth segment of lessons covering covalent bonding is going to extend into the ions and the expanded octets that can occur. The slide on polyatomic ions, which I've gotten started with the math for you, is going to involve adjusting the A value to account for the ion charge value. And also, as you're looking at these particular molecules, you're going to notice that they are ions that follow the pattern of what we learned to name back in our naming unit. So we have sulfite and ammonium. And as we've gone through and done some of the math, starting with the sulfite, as we look, because of the fact that sulfite has a charge of -2, we have to take those 2 electrons and add them in to the available electrons for our structure, and then subtract from there. So 32 minus 26 will give us 6, which is going to tell us that we have 3 bonds. 26 minus 6 is 20 lone electrons. And then from there we can draw our structure. Sulfur in the middle. Look for symmetry by drawing our 3 oxygens in a symmetrical fashion. 3 bonds. 1, 2, 3. 20 lone electrons. Okay, now to get it to an octet, each oxygen, they're all identical, needs 6. By placing the 6 electrons around the oxygens, that's going to take care of 18 of the electrons, but that means that we still have 2 left over. The remaining 2 will go on the central sulfur. With ions, we want to put our bracket around it and then indicate the ion charge, which in this case was the -2. As we move over to ammonium, N is 16, A happens to be 9, which is an odd number. This time our ion charge is a cation, which means that we're going to subtract that electron to give us an available number of 8 because we've lost an electron. 16 minus 8 is then 8 shared electrons, in other words, 4 bonds. Something else that you haven't seen at this point is that when you go to subtract the A and the S values, you end up with 0 lone electrons. Nitrogen in the middle, 4 single bonds to each of the 4 hydrogens. Place our brackets, and then put it to the +1 charge to indicate the ion. So with resonance structures, and you may have noticed that whenever I did an earlier example problem, I ended up with a double bond on one atom and a single bond on another. And I'd like to show you what can happen with those. So I've gone ahead and done the NASIS calculations for NO3 nitrate and sulfur dioxide. And you can certainly pause the video at this point to write down the math and look at what happens when we draw our structures. So in the case of NO3 to the -1, one of my oxygens is going to end up double bonded because I have calculated that I have 4 bonds. So I have to account for that. And then when I go to place my 16 electrons, the single bonded oxygens, okay, which just arbitrarily are these 2, end up with 6 lone electrons, while the double bonded oxygen ends up with 4. Perfectly valid. You do not have to worry about where you put the double bond or the single bonds, as long as you have your number of lone electrons placed correctly. Now, the concept of a resonance structure simply means that you can take the skeletal part of the structure. Okay, so here's our original structure, and the skeletal part would take all of the single bonds. To represent the double bond, we use a dashed line. Because of the fact that you're showing the double bond as alternating, we are not 100% sure of where any of the lone electrons are. So we just leave the lone electrons alone. We don't put any around them. And we call this the summary structure. SO2, you will see something similar. Sulfur in the middle. One of the oxygens is double bonded, one of them is single bonded. To the single bonded oxygen, it needs 6 lone electrons. The double bonded oxygen needs 4. Now, again, there happens to be 2 lone electrons left over. They're going to go on the sulfur. Okay, so there's your original structure. Okay, now, to show the summary structure of that, take your skeletal structure with the single bonds, represent the double bond as a dashed line. To the bonded oxygens, you do not need to put the lone electrons. However, the 2 lone electrons that were on the sulfur as the central atom have to remain intact. So these little guys right here are lone electrons that need to be maintained. The last portion of bonding is what's called the expanded octet. And everything works exactly the same with an expanded octet as what you have already seen, except that whenever you go to calculate your shared electrons, which is your S value, you will not have enough bonds to account for the number of atoms. So as you can see from this example, xenon with 2 fluorines. So Fe and then 2 fluorines, F2. And I've gone down and I've calculated right here for my shared electrons that I only have 1 bond. Well, I have 2 fluorines. What I'm allowed to do is basically to move electrons around. I need, instead of having 1 bond, I need to have 2 bonds. If I need to have 2 bonds, I can change that. In order to have 2 bonds, this needed to be a 4. So that gives me the 2 bonds that I need with my structure. Okay, now, since I adjusted this to a 2 and this value to a 4, I'm going to keep that as such. And when I go to subtract my A value of 22, I'm now going to subtract my new adjusted value of S, which is 4, to give me 18 electrons, which needs to be placed. Each fluorine to get to an octet needs 6. Okay, by doing that, I just used 12 electrons out of the 18 that I have ready to go. I have 6 left over. Okay, now, as I place the 6 electrons that are left over, I need to keep them, again, in pairs. And that would be appropriate. Okay, so I now have 1, 2, 3 pairs or 3 regions around the xenon. Here's another example, SF6. As I've gone through and calculated this, notice that my shared electrons have ended up only allowing for me to have 4 bonds. But when I look at my molecule, I have 6 fluorines. Sulfur in the middle, 6 fluorines. Okay, now we're going to do the same thing that we did on the other problem. If I need 6 bonds, I'm going to adjust this 4 to become a 6. By doing this, the 8 needs to be a 12. When I go to subtract, the original A value of 48 is fine. I'm going to subtract my adjusted value of 12 to give me 36 lone electrons. So now I have 6 bonds. 1, 2, 3, 4, 5, 6. I have 36 electrons. Each fluorine to get to an octet is going to need 6 to get to that point. And my sulfur is expanded. Perfectly legitimate and fine. The last type of problem that you may encounter is when the A and the S values both have to be adjusted, as in the example IBR4. So you will notice that I have calculated N to be 40, A is 36. Notice that I do have an ion of minus 1, so I've accounted for that. And I've gone and subtracted 40 minus 36 to get 4, which tells me that I have 2 bonds. But when I look at my structure, I have 4 bromines. My iodine is the least electronegative, so put it in the middle. I have 4 bromines, but only 2 bonds. So let's adjust. I have 4 bromines, so this needs to be a 4, thus that needed to be an 8. Then take my 36, subtract my 8 to get 28 lone electrons. Draw your bonds. 1, 2, 3, 4. Okay, so that is taken care of. 28 lone electrons. Each of the bromines needs 6 to get to the octet. Okay, now by doing that, that was 24, meaning that I have 4 electrons left over. Just like you saw in a previous problem, those are going to go on the central iodine. Keep them in pairs. 1, 2, 3, 4. And this concludes the video lessons on covalent bonding.